Jupiter is the fifth planet from the Sun and the largest in the Solar System. It is a gas giant with a mass, more than 2.5 times that of all the other planets in the Solar System combined. But a little less than 1,000th the mass of the Sun. Jupiter is the third brightest natural object in the Earth's night sky after the Moon and Venus. It has been observed since prehistoric times and is named after the Roman god Jupiter, the king of the gods, because of its massive size. Jupiter is primarily composed of hydrogen, but helium comprises 1/4 of its mass and 1/10 of its volume. It likely has a rocky core of heavier elements, 17, but like the other giant planets, Jupiter lacks a well-defined solid surface. The ongoing contraction of its interior generates heat greater than the amount received from the Sun. Because of its rapid rotation, the planet's shape is that of an oblate spheroid. It has a slight but noticeable bulge around the equator. The outer atmosphere is visibly segregated into several bands at different latitudes, with turbulence and storms along their interacting boundaries. A prominent result of this is the Great Red Spot, a giant storm that is known to have existed since at least the 17th century, when it was first seen by telescope. 800 million kilometers long, covering the entire distance to Saturn's orbit. Jupiter has almost 100 known moons and possibly many more, 18, including the 4 large Galilean moons discovered by Galileo Galilei in 1610. Ganymede, the largest of these, has a diameter greater than that of the planet Mercury. Pioneer 10 was the first spacecraft to visit Jupiter, making its closest approach to the planet in December 1973. 19. Jupiter has since been explored on a number of occasions by robotic spacecraft, beginning with the Pioneer and Voyager flyby missions from 1973 to 1979, and later by the Galileo orbiter, which arrived at Jupiter in 1995. 20. In 2007, Jupiter was visited by the New Horizons probe, which used Jupiter's gravity to increase its speed and bend its trajectory en route to Pluto. The latest probe to visit the planet, Juno, entered orbit around Jupiter in July 2016. 21. 22. Future targets for exploration in the Jupiter system include the probable ice-covered liquid ocean of the moon Europa. Main article: Grand Tack hypothesis. See also. Formation and evolution of the Solar System. Jupiter is most likely the oldest planet in the Solar System. 23. Current models of Solar System formation suggest that Jupiter formed at or beyond the snow line, a distance from the early Sun where the temperature is sufficiently cold for volatiles such as water to condense into solids. 24. It first assembled a large solid core before accumulating its gaseous atmosphere. As a consequence, the core must have formed before the solar nebula began to dissipate after 10 million years. Formation models suggest Jupiter grew to 20 times the mass of the Earth in under a million years. The orbiting mass created a gap in the disk, thereafter slowly increasing to 50 Earth masses in 3 to 4 million years. According to the Grand Tack hypothesis, Jupiter would have begun to form at a distance of roughly 3.5 astronomical units. As the young planet accreted mass, interaction with the gas disk orbiting the Sun and orbital resonances with Saturn, 24, caused it to migrate inward. 25. This would have upset the orbits of what are believed to be super-Earths orbiting closer to the Sun, causing them to collide destructively. Saturn would later have begun to migrate inwards too, much faster than Jupiter. leading to the two planets becoming locked in a 3:2 mean motion resonance at approximately 1.5 astronomical units. This in turn would have changed the direction of migration, causing them to migrate away from the Sun and out of the inner system to their current locations. 26. These migrations would have occurred over an 800,000-year time period. 25. With all of this happening over a time period of up to 6 million years after Jupiter began to form, 3 million being a more likely figure. 27. This departure would have allowed the formation of the inner planets from the rubble, including Earth. However, the formation timescales of terrestrial planets resulting from the Grand Tack hypothesis appear inconsistent with the measured terrestrial composition. 29. Moreover, the likelihood that the outward migration actually occurred in the solar nebula is very low. 30. In fact, some models predict the formation of Jupiter's analogues whose properties are close to those of the planet at the current epoch. 31. Other models have Jupiter forming at distances much further out, such as 18 astronomical units. 32. 33. In fact, based on Jupiter's composition, researchers have made the case for an initial formation outside the molecular nitrogen N2 snowline, which is estimated at 20 to 30 astronomical units. 34. 35. And possibly even outside the Argon snowline, which may be as far as 40 astronomical units. Having formed at one of these extreme distances, Jupiter would then have migrated inwards to its current location. This inward migration would have occurred over a roughly 700,000-year time period. 32. 33. During an epoch approximately 2 to 3 million years after the planet began to form. Saturn, Uranus and Neptune would have formed even further out than Jupiter, and Saturn would also have migrated inwards. Physical characteristics: Jupiter is one of the four gas giants, being primarily composed of gas and liquid rather than solid matter. It is the largest planet in the Solar System, with a diameter of 142,984 kilometers, 88,846 miles, at its equator. 36. The average density of Jupiter, 1.326 grams. Main article: Jupiter mass. Jupiter's diameter is 1 order of magnitude smaller, times 0.10045, than that of the Sun, and 1 order of magnitude larger, times 10.9733, than that of Earth. The Great Red Spot is roughly the same size as Earth. Jupiter's mass is 2.5 times that of all the other planets in the Solar System combined. This is so massive that its barycenter with the Sun lies above the Sun's surface at 1.068 solar radii from the Sun's center. 44. Jupiter is much larger than Earth and considerably less dense. Its volume is that of about 1,321 Earths, but it is only 318 times as massive. 7. 45. Jupiter's radius is about 1/10 the radius of the Sun. 46. And its mass is 1,000th the mass of the Sun. So the densities of the two bodies are similar. 47. A Jupiter mass, mj or mj up, is often used as a unit to describe masses of other objects, particularly extrasolar planets and brown dwarfs. For example, the extrasolar planet HD 209,458b has a mass of 0.69 megajoules, while Kappa Andromedae b has a mass of 12.8 m. Above the layer of metallic hydrogen lies a transparent interior atmosphere of hydrogen. At this depth, The pressure and temperature are above molecular hydrogen's critical pressure of 1.3 megapascals and critical temperature of only 33 K, 64, in this state. There are no distinct liquid and gas phases. Hydrogen is said to be in a supercritical fluid state. It is convenient to treat hydrogen as gas extending downward from the cloud layer to a depth of about 1,000 kilometers, 54, and as liquid in deeper layers. Physically, there is no clear boundary. The gas smoothly becomes hotter and denser as depth increases. 65, 66. Rain-like droplets of helium and neon precipitate downward through the lower atmosphere, depleting the abundance of these elements in the upper atmosphere. 42, 67. Calculations suggest that helium drops separate from metallic hydrogen at a radius of 60,000 kilometers, 11,000 kilometers below the cloud tops, and merge again at 50,000 kilometers, 22,000 kilometers beneath the clouds. 68. Rainfalls of diamonds have been suggested to occur, as well as on Saturn. 69, and the ice giants Uranus and Neptune. 70. The temperature and pressure inside Jupiter increase steadily inward. This is observed in microwave emission and required because the heat of formation can only escape by convection. At the pressure level of 10 bars, 1 megapascal, the temperature is around 340 K, 67 degrees Celsius. 152 degrees Fahrenheit. The hydrogen is always supercritical, that is, it never encounters a first-order phase transition, even as it changes gradually from a molecular fluid to a metallic fluid at around 100 to 200 gigapascals, where the temperature is perhaps 5,000 K, 4,730 degrees Celsius. 8,540 degrees Fahrenheit. The temperature of Jupiter's diluted core is estimated at around 20,000 K, 19,700 degrees Celsius, 35,500 degrees Fahrenheit, or more, with an estimated pressure of around 4,500 gigapascals, 71, atmosphere. Cloud layers. South polar view of Jupiter. Enhanced color view of Jupiter's southern storms. Jupiter is perpetually covered with clouds composed of ammonia crystals, and possibly ammonium hydrosulfide. The clouds are in the tropopause and are in bands of different latitudes, known as tropical regions. These are subdivided into lighter-hued zones and darker belts. The interactions of these conflicting circulation patterns cause storms and turbulence. Wind speeds of 100 meters per second, 360 kilometers. The orange and brown colors in the clouds of Jupiter are caused by upwelling compounds that change color when they are exposed to ultraviolet light from the sun. The exact makeup remains uncertain, but the substances are thought to be phosphorus, sulfur, or possibly hydrocarbons. 54, 81. These colorful compounds, known as chromophores, mix with the warmer lower deck of clouds. The zones are formed when rising convection cells form crystallizing ammonia that masks out these lower clouds from view. 82. Jupiter's low axial tilt means that the poles always receive less solar radiation than the planet's equatorial region. Convection within the interior of the planet transports energy to the poles, balancing out the temperatures at the cloud lay. Great Red Spot and other vortices. The best-known feature of Jupiter is the Great Red Spot, 83, a persistent anticyclonic storm located 22 degrees south of the equator. It is known to have existed since at least 1831, 84, and possibly since 1665, 85, 86. Images by the Hubble Space Telescope have shown as many as 2 red spots adjacent to the Great Red Spot. 87, 88. The storm is visible through Earth-based telescopes with an aperture of 12 cm or larger. 89. The oval object rotates counterclockwise, with a period of about 6 days. 90. The maximum altitude of this storm is about 8 kilometers, 5 miles, above the surrounding cloud tops. 91. The spot's composition and the source of its red color remain uncertain. Although photodissociated ammonia reacting with acetylene is a robust candidate to explain the coloration. The Great Red Spot is larger than the Earth. 93. Mathematical models suggest that the storm is stable and will be a permanent feature of the planet. 94. However, it has significantly decreased in size since its discovery. Initial observations in the late 1800s showed it to be approximately 41,000 kilometers, 25,500 miles, across. By the time of the Voyager flybys in 1979, the storm had a length of 23,300 kilometers, 14,500 miles, and a width of approximately 13,000 kilometers, 8,000 miles. 95. Hubble observations in 1995 showed it had decreased in size to 20,950 kilometers, 13,020 miles. And observations in 2009 showed the size to be 17,910 kilometers, 11,130 miles. As of 2015, the storm was measured at approximately 16,500 by 10,940 kilometers, 10,250 by 6,800 miles. 95. And was decreasing in length by about 930 kilometers, 580 miles, per year. Center and 8 others around it. While its southern counterpart also consists of a center vortex but is surrounded by 5 large storms and a single smaller one. 97. These polar structures are caused by the turbulence in Jupiter's atmosphere and can be compared with the hexagon at Saturn's North Pole. In 2000, an atmospheric feature formed in the southern hemisphere that is similar in appearance to the Great Red Spot, but smaller. This was created when smaller, white oval-shaped storms merged to form a single feature. These 3 smaller white ovals were first observed in 1938. The merged feature was named Oval BA and has been nicknamed Red Spot Jr. It has since increased in intensity and changed from white to red. In April 2017, a great cold spot was discovered in Jupiter's thermosphere at its north pole. This feature is 24,000 kilometers, 15,000 miles, across, 12,000 kilometers, 7,500 miles, wide, and 200 degrees Celsius, 360 degrees Fahrenheit, cooler than surrounding material. While this spot changes form and intensity over the short term, it has maintained its general position in the atmosphere for more than 15 years. It may be a giant vortex similar to the Great Red Spot, and appears to be quasi-stable like the vortices in Earth's thermosphere. Interactions between charged particles generated from Io and the planet's strong magnetic field likely resulted in redistribution of heat flow, forming the spot. Jupiter's magnetic field is 14 times stronger than Earth's, ranging from 4.2 Gauss, 0.42 mt, at the equator to 10 to 14 Gauss, 1.0 to 1.4 mt, at the poles, making it the strongest in the Solar System, except for sunspots. 82. This field is thought to be generated by eddy currents, swirling movements of conducting materials, within the liquid metallic hydrogen core. The volcanoes on the Moon Io emit large amounts of sulfur dioxide, forming a gas torus along the Moon's orbit. The gas is ionized in the magnetosphere, producing sulfur and oxygen ions. They, together with hydrogen ions originating from the atmosphere of Jupiter, form a plasma sheet in Jupiter's equatorial plane. The plasma in the sheet co-rotates with the planet, causing deformation of the dipole magnetic field into that of a magnetodisk. Electrons within the plasma sheet generate a strong radio signature that produces bursts in the range of 0.6 to 30 MHz, which are detectable from Earth with consumer-grade shortwave radio receivers. At about 75 Jupiter radii from the planet, the interaction of the magnetosphere with the solar wind generates a bow shock. Surrounding Jupiter's magnetosphere is a magnetopause, located at the inner edge of a magnetosheath, a region between it and the bow shock. The solar wind interacts with these regions, elongating the magnetosphere on Jupiter's lee side and extending it outward until it nearly reaches the orbit of Saturn. The four largest moons of Jupiter all orbit within the magnetosphere, which protects them from the solar wind. 54. The magnetosphere of Jupiter is responsible for intense episodes of radio emission from the planet's polar regions. Volcanic activity on Jupiter's moon Io injects gas into Jupiter's magnetosphere, producing a torus of particles about the planet. As Io moves through this torus, the interaction generates alphen waves that carry ionized matter into the polar regions of Jupiter. As a result, radio waves are generated through a cyclotron maser mechanism, and the energy is transmitted out along a cone-shaped surface. When Earth intersects this cone, the radio emissions from Jupiter can exceed the solar radio output. 5 minutes longer than that of the equatorial atmosphere. 3 systems are used as frames of reference, particularly when graphing the motion of atmospheric features. System I applies to latitudes from 10 degrees north to 10 degrees south. Its period is the planet's shortest, at 9 hours 50 minutes 30.0 seconds. System 2 applies at all latitudes north and south of these. Its period is 9 hours 55 minutes 40.6 seconds. System 3 was defined by radio astronomers and corresponds to the rotation of the planet's magnetosphere. Its period is Jupiter's official rotation. Observation conjunction of Jupiter and the Moon. The retrograde motion of an outer planet is caused by its relative location with respect to Earth. Jupiter is usually the fourth brightest object in the sky, after the Sun. The Moon, and Venus, 82, at opposition Mars can appear brighter than Jupiter. Depending on Jupiter's position with respect to the Earth, it can vary in visual magnitude from as bright as -2.94, 13, at opposition down to 13, -1.66 during conjunction with the Sun. The mean apparent magnitude is -2.20 with a standard deviation of 0.33, 13. The angular diameter of Jupiter likewise varies from 50.1 to 29.8 arcseconds. 7. Favorable oppositions occur when Jupiter is passing through perihelion, an event that occurs once per orbit. 110. Because the orbit of Jupiter is outside that of Earth, the phase angle of Jupiter as viewed from Earth never exceeds 11.5 degrees. Thus, Jupiter always appears nearly fully illuminated when viewed through Earth-based telescopes. It was only during spacecraft missions to Jupiter that crescent views of the planet were obtained. 111. A small telescope will usually show Jupiter's 4 Galilean moons and the prominent cloud belts across Jupiter's atmosphere. 112. A large telescope will show Jupiter's great red spot when it faces Earth. Pre-telescopic research model in the Almagest of the longitudinal motion of Jupiter relative to Earth. Observation of Jupiter dates back to at least the Babylonian astronomers of the 7th or 8th century BC. 114. The ancient Chinese knew Jupiter as the Tsui star, Suxing Sui Xing, and established their cycle of 12 earthly branches based on its approximate number of years. The Chinese language still uses its name, simplified as Sui, when referring to years of age. By the 4th century BC, these observations had developed into the Chinese zodiac. 115, with each year associated with a Tai Sui star and god controlling the region of the heavens opposite Jupiter's position in the night sky. These beliefs survive in some Taoist religious practices and in the East Asian zodiac's 12 animals, now often popularly assumed to be related to the arrival of the animals before Buddha. The Chinese historian Shi Zizong has claimed that Ganda, an ancient Chinese astronomer, reported a small star in alliance with the planet 116, which may indicate a sighting of one of Jupiter's moons with the unaided eye. If true, this would predate Galileo's discovery by nearly 2 millennia. 117, 118. A 2016 paper reports that trapezoidal rule was used by Babylonians before 50 BCE for integrating the velocity of Jupiter along the ecliptic. 119, in his 2nd century work The Almagest, the Hellenistic astronomer Claudius Ptolemaeus constructed a geocentric planetary model based on deferents and epicycles to explain Jupiter's motion relative to Earth, giving its orbital period around Earth is 4,332.38 days, or 11.86 years. 120. In 1610, Italian polymath Galileo Galilei discovered the 4 largest moons of Jupiter, now known as the Galilean moons, using a telescope. Thought to be the first telescopic observation of moons other than Earth's. One day after Galileo, Simon Marius independently discovered moons around Jupiter. Though he did not publish his discovery in a book until 1614, 121, it was Marius's names for the major moons, however, that stuck: Io, Europa, Ganymede, and Callisto. These findings were the first discovery of celestial motion not apparently centered on Earth. The discovery was a major point in favor of Copernicus' heliocentric theory of the motions of the planets. Galileo's outspoken support of the Copernican theory led to him being tried and condemned by the Inquisition. 122, during the 1660s. Giovanni Cassini used a new telescope to discover spots and colorful bands, observe that the planet appeared oblate, and estimate the planet's rotation period. 123. In 1690 Cassini noticed that the atmosphere undergoes differential rotation. 54. The Great Red Spot may have been observed as early as 1664 by Robert Hooke and in 1665 by Cassini. Although this is disputed, the pharmacist Heinrich Schwabe produced the earliest known drawing to show details of the Great Red Spot in 1831. 124. The red spot was reportedly lost from sight on several occasions between 1665 and 1708 before becoming quite conspicuous in 1878. It was recorded as fading again in 1883 and at the start of the 20th century. Both Giovanni Borelli and Cassini made careful tables of the motions of Jupiter's moons, allowing predictions of when the moons would pass before or behind the planet. By the 1670s, it was observed that when Jupiter was on the opposite side of the Sun from Earth, these events would occur about 17 minutes later than expected. Ole Romer deduced that light does not travel instantaneously, a conclusion that Cassini had earlier rejected, 40, and this timing discrepancy was used to estimate the speed of light, 126, in 1892. E. Barnard observed a fifth satellite of Jupiter with the 36-inch, 910 mm, refractor at Lick Observatory in California. This moon was later named Amalthea. 127. It was the last planetary moon to be discovered directly by visual observation. 128. An additional 8 satellites were discovered before the flyby of the Voyager 1 probe in 1979. D. Infrared image of Jupiter taken by ESO's Very Large Telescope in 1932. Rupert Wilt identified absorption bands of ammonia and methane in the spectra of Jupiter. 129. 3 long-lived anticyclonic features termed white ovals were observed in 1938. For several decades they remained as separate features in the atmosphere, sometimes approaching each other but never merging. Finally, 2 of the ovals merged in 1998, then absorbed the third in. Both Giovanni Borelli and Cassini made careful In 1955, Bernard Burke and Kenneth Franklin detected bursts of radio signals coming from Jupiter at 22.2 MHz. 54. The period of these bursts matched the rotation of the planet. And they used this information to refine the rotation rate. Radio bursts from Jupiter were found to come in 2 forms: long bursts, or L bursts, lasting up to several seconds, and short bursts, or S bursts, lasting less than 1/100th of a second. 131. Scientists discovered that there are 3 forms of radio signals transmitted from Jupiter. Decametric radio bursts, with a wavelength of tens of meters, vary with the rotation of Jupiter, and are influenced by the interaction of Io with Jupiter's magnetic field. 132. Decimetric radio emission, with wavelengths measured in centimeters, was first observed by Frank Drake and Hein Havatum in 1959. 54. The origin of this signal was a torus-shaped belt around Jupiter's equator. This signal is caused by cyclotron radiation from electrons that are accelerated in Jupiter's magnetic field. 133. Thermal radiation is produced by heat in the atmosphere of Jupiter. In 1955, Bernard Burke and Kenneth Franklin detected bursts of radio signals coming from Jupiter at 22.2 MHz. 54. The period of these bursts matched the rotation of the planet, and they used this information to refine the rotation rate. Radio bursts from Jupiter were found to come in 2 forms: long bursts, or L bursts, lasting up to several seconds, and short bursts, or S bursts, lasting less than 1/100th of a second. 131. Scientists discovered that there are 3 forms of radio signals transmitted from Jupiter. Decametric radio bursts, with a wavelength of tens of meters, vary with the rotation of Jupiter, and are influenced by the interaction of Io with Jupiter's magnetic field. 132. Decimetric radio emission, with wavelengths measured in centimeters, was first observed by Frank Drake and Hein Havartem in 1959-54. The origin of this signal was a torus-shaped belt around Jupiter's equator. This signal is caused by cyclotron radiation from electrons that are accelerated in Jupiter's magnetic field. 133. Thermal radiation is produced by heat in the atmosphere of Jupiter. Since 1973, a number of automated spacecraft have visited Jupiter, most notably the Pioneer 10 space probe. The first spacecraft to get close enough to Jupiter to send back revelations about its properties and phenomena. 134, 135 flights to planets within the Solar System are accomplished at a cost in energy, which is described by the net change in velocity of the spacecraft, or delta V. Entering a Hohmann transfer orbit from Earth to Jupiter from low Earth orbit requires a delta V of 6.3 kilometers. Flyby missions spacecraft closest approach distance Pioneer 10 December 3, 1973 130,000 kilometers Pioneer 11 December 4, 1974 34,000 kilometers Voyager 1 March 5, 1979 349,000 kilometers Voyager 2 July 9, 1979 570,000 kilometers Ulysses February 8, 1992 139 408,894 kilometers February 4, 2004 139 120 million kilometers Cassini December 30, 2010 million kilometers New Horizons February 28, 2007 2,304,535 kilometers beginning in 1973. Several spacecraft have performed planetary flyby maneuvers that brought them within observation range of Jupiter. The Pioneer missions obtained the first close-up images of Jupiter's atmosphere and several of its moons. They discovered that the radiation fields near the planet were much stronger than expected. But both spacecraft managed to survive in that environment. The trajectories of these spacecraft were used to refine the mass estimates of the Jovian system. Radio occultations by the planet resulted in better measurements of Jupiter's diameter and the amount of polar flattening. 6 years later, the Voyager missions vastly improved the understanding of the Galilean moons and discovered Jupiter's rings. They also confirmed that the Great Red Spot was anticyclonic. Comparison of images showed that the red spot had changed hue since the Pioneer missions, turning from orange to dark brown. A torus of ionized atoms was discovered along Io's orbital path. And volcanoes were found on the Moon's surface, some in the process of erupting. As the spacecraft passed behind the planet, it observed flashes of lightning in the night-side atmosphere around the Sun. During this pass, the spacecraft studied Jupiter's magnetosphere. Ulysses has no cameras, so no images were taken. A second flyby 6 years later was at a much greater distance, 139. In 2000, the Cassini probe flew by Jupiter on its way to Saturn and provided higher resolution images. 142. The New Horizons probe flew by Jupiter in 2007 for a gravity assist en route to Pluto. 143. The probe's cameras measured plasma output from volcanoes on Io and studied all 4 Galilean moons in detail, as well as making long-distance observations of the outer moons Himalaya and Alara. The first spacecraft to orbit Jupiter was the Galileo probe, which entered orbit on December 7, 1995. 50. It orbited the planet for over 7 years. conducting multiple flybys of all the Galilean moons and Amalthea. The spacecraft also witnessed the impact of comet Shoemaker-Levy 9 as it approached Jupiter in 1994, giving a unique vantage point for the event. Its originally designed capacity was limited by the failed deployment of its high-gain radio antenna. Although extensive information was still gained about the Jovian system from Galileo 145, a 340 kg titanium atmospheric probe was released from the spacecraft in July 1995. Entering Jupiter's atmosphere on December 7, 50, it parachuted through 150 kilometers, 93 miles, of the atmosphere at a speed of about 2,575 kilometers. NASA's Juno mission arrived at Jupiter on July 4, 2016, and was expected to complete 37 orbits over the next 20 months. 21. The mission plan called for Juno to study the planet in detail from a polar orbit. 147, on August 27, 2016. The spacecraft completed its first flyby of Jupiter and sent back the first ever images of Jupiter's North Pole. 148. Juno would complete 12 science orbits before the end of its budgeted mission plan, ending July 2018. 149. In June of that year, NASA extended the mission operations plan to July 2021, and in January of that year the mission was extended to September 2025 with 4 lunar flybys. 1 of Ganymede, 1 of Europa, and 2 of Io. 150, 151. When Juno reaches the end of the mission, it will perform a controlled deorbit and disintegrate into Jupiter's atmosphere. During the mission, the spacecraft will be exposed to high levels of radiation from Jupiter's magnetosphere, which may cause future failure of certain instruments and risk collision with Jupiter's moons.